Hi, welcome back. In this chapter, or in this unit 3, we covered topics from 3 chapters, chapters 8, 9, and 10. In chapter 8, meaning unit 3.8, we'll talk about some basics of data summary. Let's get started. Okay, these are the outcomes for this particular unit slash chapter 3.8 or chapter 8. First, we'll talk about a brief introduction of what data summary is. Remember, we already talked about how to search for, identify, locate, access, download, and run the data checks and clean the data. Now, once you have this clean data, you need to be able to summarize it or analyze it. And first part of it is actually trying to make sense of this data that's in a correct format now. First, we'll talk about some basics of it. And this is where I'll talk about some statistical um, basic information, followed by descriptive statistics. Here also I'll cover some statistics basics specific to descriptive statistics. Followed by that, we'll talk about two important kind of comparisons, a general comparison and there is a benchmark. We'll talk more about these. So these are the things, and followed by an optional applicational exercise. Okay, coming to some basics, the introduction to summarizing data. Remember, in the previous units, we talked about how to identify, locate, then download the data, followed by running some integrity checks to see how good or bad the data is, followed by cleaning it. Now, the next step is to analyze the data. This is where you try to convert the raw data into some meaningful format. So summarizing data then, or analyzing data, is primarily a way of generating meaning or meaningful information from the collected data or the access data. So, um, so it is like creating meaning out of meaningless data. That's what summarizing or evaluation, analyzing data means. Now, mostly we'll use Excel or other spreadsheet kind programs, primarily Excel. And in doing so, we'll talk about some formulae and how you can use that to run some basic summarizing or statistics. And also we use summarizing techniques similar to pivot tables that we looked at in data integrity checks unit. Now, here are the true things. When you're analyzing data, there are two aspects of analyzing data. Now, bear with me here for a second. I want to give you a very brief distinction between these two ways of analyzing data. One is the called the summary statistics. The other one is called the inferential statistics. Summary statistics is often referred to as the descriptive statistics. The purpose of summary statistics is to describe any meaningful patterns from within the data that you have obtained. It describes anything. It does not generate any or create any new information or inferences about the population. Again, it will make more sense once we go to the next slide. We'll try to make clear description about what inferential statistics is. Just another way to look at summary statistics and inferential statistics, the difference between these two is that summary statistics are the statistics that you will run from the data that you have gained from other sources, so secondary data, if you remember. So we'll look at things like doing counts, sums, totals, averages, and so on and so forth. So summary statistics are done on secondary data, and that's what this class is about: summary statistics or descriptive statistics. Inferential statistics, on the other hand, is the data that researchers primarily interested in making inferences about the population in general. So they do the inferential statistics. So they work on the primary data. They control how the data is collected. Then the collected data is then analyzed to make inferences about the population. Again, it will make sense what I mean by inferences about the population in the next slide. An example for that, so you need primary data for that. An example for that is the Gallup polls during elections. Then how they make predictions about who is going to win by randomly selecting individuals across different states and then making predictions or inferences about who is going to win. And such kind of analysis is the inferential statistics. And we are not doing that. We use already collected data that we don't have control over and just try to describe the information provided in the data in order to answer the questions that we start with, if you remember that. Okay, so let's talk about the subtle difference between these two kinds of statistics, a summary and inferential, in the next slide. Okay, so coming to the difference between descriptive statistics and inferential statistics. Now, let's look at the inferential statistics and try to understand what it is. Now, researchers collect primary data. They collect primary data and they collect data because they have a question. Now, these are the question of not of the sort that we ask primarily based on summary statistics. To some extent, they're related, but we're talking about research questions about population. And you're interested in understanding or have questions about population in general. For instance, let's take the example. Your question is about an opinion of people, right, on death penalty. Okay. Now, you need to know what percentage of people are in favor of death penalty. Now, one way to do that is to kind of use something like census to ask each and every individual in this population, let's say United States, ask this question, then see how many of those individuals are in favor, then calculate the percentage, then you have the answer. But that's a very painful, resourceful, time demanding process, right? What inferential statistics does is it gives the tools of inferring information about the population just based on the data you've collected from a subset of that population called sample. So you have the entire population of the United States, and the question you're interested in is about a specific variable. And these questions are invariably about variables. Here, the variable is opinion about favorable opinion about the death penalty, or majority of people in favor of death penalty. So then you randomly select a sample of, say, 1,000 individuals. So the size of the sample is 1,000. And then you ask them the question, are you in favor or not of death penalty? Let's assume that you have data from these 1,000 individuals, right? And they answered this question about whether you are in favor, yes or no. Let's say that out of these 1,000 individuals, 600 individuals said that they are in favor of death penalty, and 400 said they are in not in favor of death penalty. So 600 out of 1,000 is 60%. So 60% of the sample said they are in favor of death penalty. So you have your question. Do majority of people in the United States are in favor of death penalty? It seems like yes, 60%. But keep in mind, this question is not about just these 1,000 individuals, right? This question is about the population overall. So now the question is, now given it is 60% for this particular sample, right? Can you now infer that it would be 60% for the entire population? The answer is no. Why? Let's say You randomly select another 1,000 individuals, right? Then ask them the same question. What do you think these values would be? Do you think you'll have same 60%, 600 individuals saying yes and 400 individuals saying no? No, it will change. It will be different each time you collect data. Maybe it's 65% next time. Another time you do the same thing, maybe it's 75%. It keeps changing. But here is the beauty of it. Based on how it will change and based on the size of the sample, you can actually go from this 60%, which is a sample statistic, right, and make inferences about the population by using inferential statistics. So what is inferential statistics doing here? It is inferring about the population values of a variable based on the sample values. So sample values are like statistics, summary statistics. Population values are the inferential statistics. And for you to go from these sample values to population values, you use a magic wand called probability. So let me elaborate on that. We found that in our sample of 1,000 individuals, 60% are in favor, right? Now you use this magic wand to make inferences about the population, and by using these inferential statistics, you will infer, you will estimate the population value. Right, sample value was 60% are in favor, right? The population value would be something like, well, with some level of confidence, you would say, well, I'm 95% confident that the population value based on the sample value of 60% with a sample size of 1,000 is 95% confident that it will fall somewhere between 55% and 65%. You see that? This estimation is inferencing. You're estimating the population values based on the sample values with certain degree of certainty, then your estimation comes in a range. That is inferential statistics. And this class is not about this inferential statistics, right? This class is primarily about the summary statistics, not of the sample summaries, but of the data collected in a given county. So it's at the population level, but it's specific to the data. We don't have any control over collection of the data. So I hope you understand. And there is this statement I like, that I just generated. It is to say that making inferences is all about variables. Researchers ask questions about variables in the population, then they answer questions by using inferences, and they answer questions about variables in the population. It's all about variables. You'll also learn later that even statistics, some summary statistics that we work on, the data we obtain from different websites, is also about variables. Is also about variables. Just think about it. You worked on different data files. You've downloaded different data sets, right? What do you think the data has? The data file has information about, say, individuals, right? But it has information specific to the variables of these people, right? Person X, what is his income? What is the age? So these are different variables. We'll talk more about what variables are in the next slide. Uh, okay, descriptive statistics. Now that we talked about some aspects of summarizing data, I want to give you more information about the thing that we'll do in this class using descriptive statistics. We try to describe the data, um, some meaningful patterns that you observe in the data. Now, before we talk about the different ways of summarizing, there are some basic things that you need to know, which I will talk about in the next few slides. If you remember in the earlier slides, I said that It's all about variables. It is all about variables. Now, what we'll do in the next few slides is talk about what variables are, what are the two primary kinds of variables, and how can we summarize? Remember, we're talking about summary, right? How can we summarize variables of these two kinds? That's what we'll do in the next few slides. Okay, so this is more like a primer where um, we'll touch upon some things that you might already know. So we said a variable, right? Now, what is a variable? Variable is something that is not constant. It varies. That's why it's a variable. Constant is something that is always the same. It doesn't change. A variable is something that changes either from person to person, place to place, or time to time. Any aspect of a person, place, or thing that changes is called a variable. And if you think about it, the data files, the data you collect are like data files, right? The data file has basically tables, and these tables have typically information specific to people, right? And such information include name, age, just an example, gender, height, weight, ethnicity, political affiliation, religion, GPA, shoe size, number of times they change their major in college. Now, these things are not constant. That's why these are variables. So each column in the data set is a variable, like name. That's not constant. It is different from person to person. Who knows? It may be different from to time for the same person. Age is different, right? It's not the same or constant for everyone. So age is another variable. Gender is not constant. It varies from person to person. That's a variable. Height is not constant, so that's a variable. Weight is not constant, that's a variable. Ethnicity is not the same. Wherever you have a column, that's a variable. And a variable is anything that changes, that's not constant. Now, religion, GPA, shoe size, these are all the variables. And so think of a data set as a set of columns, and each column represents a variable. That would be the best way to objectively look at the data. Now, here are the things. When we say a variable is something that is not constant, right? So this variable, it captures some information about a thing, a human, time, or place, or thing. So, for instance, this particular variable name, it carries information about all these individuals. What kind of information is that? Well, information related to the name. What kind of information does age, this variable, carry? Information about the age. What about this variable gender? Well, information about the gender, and so on and so forth. So each variable carries a specific kind of information about whatever the data points are. Usually the rows represent information specific to an observation, like a person, a place, or thing. So having said that, variables can be classified into two types. Let me repeat. The information that these variables carry can be categorized into two different kinds. One is qualitative information, qualitative information. The other one is quantitative information. Qualitative information is information that is not measurable and is more qualitative in nature. So name is a qualitative information. Age, however, is not a qualitative information. You can measure age. You cannot measure name. Gender, you cannot measure gender in a number format. So this is a qualitative variable. What about height? Just think about it. Can you measure height? Yes. So that's a quantitative variable. Now, I said there are variables of two types, right? This qualitative variable is about the quality, so that all the possible values of this quality are some kind of categories. For instance, name. Well, there are different types of names. There is no measurement to it. That's not a good example. Let's take gender. Gender has different categories, male, female. You may have more depending on how you are measuring it, right? Ethnicity has some distinct categories, right? Political affiliation has distinct categories. So let's call this qualitative variable a categorical variable. That's another name, and we'll use this name from here on. A categorical variable is a variable where the possible values of these variables are different categories. Age as category of male and female, ethnicity as category of, for example, of Caucasian, African American, and Native Americans. Political affiliation are again categories of Democrats, Republicans, Independent, and so on and so forth. Religion and so on. So these are different categories. The values are different categories. So you can also call the qualitative variable a categorical variable. The other kind of variable, so the reason is C for categorical variable and Q for quantitative variable. Just so it won't confuse you with the qualitative. So that's why quantitative, Q refers to quantitative. So age is a quantitative variable because you can measure the quantity, right? Gender, you cannot measure it. It's not a quantitative variable. Height, you can measure it. It's a quantitative variable. Weight, you can measure it. It's a quantitative variable. And GPA, you can measure it. It's in numbers. Shoe size, and the number of times you change your major is also a quantitative variable. Now, this distinction is very important because if you know what the column is that you're trying to summarize, and if you know whether it's a C or a Q, that will determine the kind of summaries you use to summarize these variables. Make sense? So identifying each column that you're trying to analyze, whether it's a C or a Q, gives an important insight into how you can analyze it. In other words, how you can summarize it. I hope this makes sense. And in the next few slides, we'll talk about, well, what if the column is a categorical variable? How can we summarize it? Then we'll talk about what if the column is a quantitative variable? How can we summarize it? And we'll do that in that order. Okay, so in this slide, we'll talk about how to summarize a variable when the variable is a categorical variable. Let's take the variable political affiliation. It's a categorical variable because it cannot be measured in numbers. It's a quality, a characteristic of different categories: Democrats, Republican, and independent, and maybe apolitical, right? Let's say we have a data file, right? And in this data file, there are 78 million observations who are Democrats, okay? So they voted for Democrats in 2020. We have 72 million observations, 78 here, 72 million here, who voted for Republicans, okay? And 15 million observations who voted for independent, and 2 million who did not vote. Yeah, let's say this is the entire population. Now, when you are summarizing categorical variable, what you do is you list all the categories and you provide raw count. How often did this category occur? 78 million times. So it's called count, number of times, or frequency. Then you do the same for the second category, third category, and fourth category. So how do you summarize a categorical variable? You list the categories and provide counts or frequency. Now the raw count or frequency doesn't make sense. So what you do is you convert the raw count or frequency into what is called as relative frequency. Okay, 78 million out of how many millions? Well, it's basically 78 million divided by, add all these up, whatever the number is, it's divided by that. So it's 72 plus 15 is 87 plus 2, 89. So 78 over 89 million would give you 46.7%. So that's called relative frequency. It's out of a standard value, which is in this case in percentage, it's out of 100. 46.7% of the population are Democrats based on the election in 2020, let's say. You do the same here, 72 divided by the entire number will give you 43% and so forth and so forth. So one way to summarize a categorical variable is through frequency. A more standardized way to summarize a categorical variable is through percentages. So yet another way of summarizing is in the form of proportion. A proportion is like percentage, but a percentage is out of 100. A proportion is out of 1. A proportion is out of 1.46 is 46.7%. So if you multiply proportion by 100, it would be percentage. Or if you divide proportion by 100, it will change into percentage. Okay, so how do you summarize a categorical variable? By listing all the categories, then presenting the raw count or frequency, and in a more standardized form, relative frequency, either in the form of percentage or in the form of proportion. Now, this is through numbers. A visual way of representing or summarizing a categorical variable is using a pie chart. So the same information can be converted into a more visual information in the form of a pie chart. So the entire pie represents the possible values. This one is the slice for Democrats. This slice represents Republicans. This slice represents independents, and this small slice represents those who did not vote. Now, depending on the count or the percentage, the slice, each slice has its own shape. So this particular slice is bigger because it is 46.7%. This is the next biggest because it is 43.1%. And this is third biggest because it is 9%. And this is the smallest because this slice only has 1.2%. You see that now? A categorical variable is summarized with the help of a pie chart. And, and the slices of the pie represent the percentage for each category, which is nothing but a relative frequency. So either it's frequency or relative frequency, and the relative frequency can be in the form of percentage or proportion. Percentage is out of 100 and proportion is out of 1. Okay, and this is exactly what this particular table says here. The kind of variable is categorical. The raw entries, which are this raw entries, these are categories. An unstandardized way of summarizing is summary statistic would be just frequency. A more standardized form of it, one way is using a relative frequency of proportion, or another standard way of summarizing it would be using a relative frequency in percentage. A more graphic way of doing it is using a pie chart, and a similar way is called bar graph, where you would have a graph with bars, and each bar represents the size of the slice of the pie, the height. The x-axis is the categories, and the y-axis would be the percentage or proportion or frequency. So that's about summarizing the categorical variable. And in the next slide, we'll take an example of a quantitative variable and how we will summarize it. Okay, now that we know how to summarize a column, if the column is represents a categorical variable. Now it's time to talk about how to summarize a column if that column is of a quantitative type. Let's look at this example. So the variable here is the number of times a college student changed his or her major. And it seems like either they did not change or changed once, twice, thrice, and so on and so forth. The max is 8. Now, there are 6,750 observations. So 6,750 college students that changed, they did not change their major. Then we have 13,550 college students who changed it once. So there are these many observations. So this is like a summarized form of it. Then 13,550 changed again twice. 9,000 changed it thrice. So total number of observation is when you count all this, sum all these things. Okay. Now, number of times someone changes a major is a quantitative variable because you can measure it in numbers, right? Now, how to summarize it? Well, the idea is quite similar to categorical variable, but it changes when it comes to summarizing. Let me explain what I mean by that. So the x-axis here represents the possible values of the variable, just like in categorical variable, you have categories, right? The categories were Democrats, Republican. Here, those are numbers: 0 times, 1 time, 2 times, 3 times, 4 times. Then each bar represents the frequency. Y-axis is frequency, right? 6,750 times, 13,550, and so on and so forth, right? So this can be a frequency. Well, similar to a categorical variable, this can also be relative frequency in terms of percentages. It can also be relative frequency in the form of proportion. But that's not an interesting thing when you're summarizing a quantitative variable. Because if it's a categorical variable, each category is distinct and you can talk about, okay, which particular category has highest frequency. So, okay, Democrats have highest frequency. It makes sense when the categories are distinct and there is no order to it. And those are not numbers, but these are numbers, right? There is some importance to the order. So you can summarize it in this fashion, but that won't yield you any meaningful information. Okay. So what is the meaningful information then? Well, a quantitative variable's meaningful information lies in measuring one number because it's all about numbers, right? One number that represents this particular variable. Well, it's something like, on average, how many times do college students change their major? We need one number that can explain and represent the quantitative variable, right? Like, what is the shoe size, average shoe size of males in the United States? That one number should represent the typical value for that variable. So when it comes to quantitative variable, the relative frequency and proportions are not so meaningful. What is meaningful is a representative number. And that representative number is nothing but a measure of center called central tendency. You might have learned that in your high school or middle school, I don't know. A measure of central tendency. There are three measures of central tendency: mean, median, and mode, right? Mean, median, and mode. Mean is when you take all the observations. Now this is 6007 have with zero observations, right? When you take all these observations, add the number of times they've changed, and divide it by total number of observations, then it gives the mean, right? Now again, you know the distinction between mean, median, and mode. I don't want to talk about that. That's not so useful as such at this point to get in detail about the subtle things that you already know. But this is what I want you to pay attention to. If it is a quantity variable, there are two important measures of central tendency, or a representative number. Um, one is median, the other one is mean. These are two important ways of measuring, representing a quantity variable. Okay, median and mean. Median is the middlemost observation. So if there are like 1 million observations here, and each observation, if you rank order them and you take the middlemost observation, whatever that value, that observation takes a value of number of times it has changed the measure, that would be the median. Okay. Mean is you add all those values, divide by total number of observations, and whatever value you get, that would be the mean. And mean is most commonly used measure of central tendency. So bottom line, when you have a quantity variable, you use mean or median, and mean is more meaningful. And just the mean or median is not sufficient. It should be also, it should be supplemented by another kind of information called the variability, or the spread, measure of spread. One is the measure of center, the other is the measure of spread. If you're using median as a measure of center, then the corresponding measure of spread is the range. What is range? Well, what is the minimum value and what is the maximum value? And the difference between those two is the range. So 0 is the minimum number of times they change their measure. 8 is the max. 8 minus 0, 8 is the range, right? A more meaningful, a more informative um, measure of spread than the range is the interquartile range. Again, we're not talking about that. It's not so important for this class. But interquartile range is also range for the middle 50% of the observation. We're not getting in there. Okay. Let's look at the other most commonly used measure of center, which is mean. And that mean is associated with commonly used measure of spread. Range is commonly used for both, but most important measure of spread is standard deviation. It is standard deviations, and you already know about means and standard deviations. Just keep in mind that when you're looking at quantity variable, you're talking about mean and standard deviation. Let me give you another example here. Let's say a colleague of mine comes to me and say, "Hey, how did your class do on the midterm exam?" Well, how do I answer that question? Well, it depends on the distribution, right? It depends on calculating that one representative center that can describe the performance of the entire class for that exam. Because exam score is a quantitative variable. That one number would be average. I would say, you know what? My students actually did well. The average was 85%, meaning that 85% performance is applicable to the entire class. Let's say they did worse. Then I say, you know what? The average is C. They scored 60%, sorry, 70%. So they didn't do well. So the mean represents that central value that represents the variable that we are talking about. And standard deviation is on average how many deviations, how different the class scores are from the mean. If I say standard deviation of 1, what I'm saying is that Well, my class performed really well. The center is 85. The average is 85 with only an standard deviation of 1. In other words, most of the values are close to 85%. If I say the standard deviation was 20, that means that although average is 85, there are a lot of variability, that there are 20 points around the mean. Again, I'm not going to get into much detail. I just want to give you an idea that whenever the variable that you're summarizing is a quantitative variable, the most commonly used of measure of center is mean, with standard deviation as the measure of spread. If median is used, which is done not so often, then you have IQRR range. But this is important to keep in mind. Um, then in terms of pictures, how do you represent it? In the form of this. This is called a histogram. It's called a histogram. If you use a median, you use a box plot. Again, we don't need to go over that, at least at this point, but a box plot is something like this, where it is talking about number of observations as opposed to the actual number. So if the column that you're trying to summarize is a quantity variable, the raw entry is in terms of numbers. Each observation either says 0 or 1 or 2 or 3 or 4 or how many ever number of times they've changed the measure. Then the other one is frequency. That's one unstandardized way to summarize it, which is not so meaningful for a quantitative variable. I have CI here representing what is called as class interval frequency or interval frequency, but I don't want to talk about that. But it is especially in cases where the values are not discrete, like not just 0 times 1, 2, 3, 4. If there are values of all possible values, 0.1, 0.2, 0.3, which is not applicable for this example, but if you take the example, say GPA, it can take any value, 1, 1.1, 1.2, 2, 2.1, 2.3, and so forth, right? So such a variable, in that case, we use interval frequency. In other ways, frequency is not an important thing for quantitative variable. What is more important is the fact that you will measure the mean and the standard deviation, and you use the histogram. Okay, so I think that is good enough of primer for you to quickly uh, rekindle your understanding of the descriptive statistics that you have learned in your high school. Okay, let's talk about comparisons. Now, this is particularly important for quantitative variables, which has numbers, right? And when you have numbers, you are not just presenting numbers of average, for instance, the average performance of my students in my class in the midterm, but you compare it with numbers from a different group. Let's say performance of students in midterm from another colleague of mine who is teaching the same class, let's say. Now, when you compare these numbers, which is usually done when you have a quantitative variable, right? There are some tools, there are some ways of making comparisons. You can compare means, you can compare different things, and I'll talk about what those are in the next slide. So, okay. So when you're comparing um, quantitative variable across different groups or different categories of a different variable, what you do is you can talk about it in terms of um, the change in numbers, in raw numbers. I call that amount change or raw change. Or you can talk about in terms of change in percentage or difference in percentage. Um, and you can also talk about percent total, and we'll talk about these three things in this slide. And in the next few slides, we'll talk about another very important construct called ratios and rates. Again, most of these things are applicable to quantitative variable, and those are the things we usually measure and summarize. Okay, so these particular numbers are taken from your textbook, and it says that in the year 2011, the federal government has spent 708.2 billion dollars on national defense. In 2012, they spent 680 million dollars, 680.4 million dollars. So I think it is reverse, but anyways, so if you're trying to see what is the difference, like how much more or less did they spend from one to another year, what you can do is subtract 680 million from one year from 708 million from the other, which will leave you with 27.8 million. So this minus this is 27.1 year. So the difference in the raw number between 2011 and 2012 in terms of expenditure on defense is how much? 27.8 millions. Well, when you say 27.8 millions, it may seem like a big amount, but it's not a standardized form of calculating the difference. When you convert into a more standardized form, it's called the percentage change, right? You try to see what is 27.8 millions. Well, it is the difference in expenditure on national defense from one year to another. But what percentage does it account for? That gives more meaningful information. So you see, what is 27.8% from 70.82%? So you basically divide this by this, multiplied by 100, then you get 3.93%. So this difference of 27 million between from one to another year, it accounts for 3.93%. So there is a percentage change of almost 4% change in expenditure on national defense from 2011 to 2012. So that's one way. One way is to change in numbers in terms of raw amount. Another way is to describe the change in number in terms of percentages. Let's talk about percent total though. Now, this is usually you do of percent of total when you are comparing numbers from same year usually, not across different years, but same year, but for different categories of expenditure. So let's say you want to know, you know that on national defense, um, United States has spent $680 million in 2012, right? The same information here. But how much is it when compared to um, expenditure on Social Security? That can give a measure of the planning of a government in terms of their expenditure, right? Well, what the first thing you need to do to calculate that is see the total. Okay, the total amount that is spent for these two is 1,453 millions, right? Million dollars. Now, the difference between these two categories for the same year is 92.8. How did I get that? This subtract this from this, you get 92.8 million um, dollars, billion dollars. Now the question is, um, the difference in percentage is pretty much same like we did before, right? You take the highest number and subtract this from the highest number, and then what do you say? Then you calculate the percentage for the highest number, basically. That will give the difference in percentage, just like we did here. But here we are talking about percent of total. What it means is that out of $14,530 million, for $1,453.6 billion, what percentage is allotted for security, social security, and what percentage is allotted for defense? So to do that, you take the amount spent on Social Security, divide it by the total amount and multiply it by 100, then you get the percent of total spent on Social Security, which is 53%. And if you do the same for defense, it will give you percent of total for the defense. So if you're comparing categories for the same year and see which one you spend more, seems like you spend a little bit more on Social Security and more, a lot, a little bit more when compared to the defense. So those kinds of comparisons will be more meaningful. Some instances when your questions are about where is government spending more? Is it domestic or international and defense. So that's called percent of total. So we talked about the amount change, percentage change, because we talk about comparisons, right? Between numbers. We also talk about percent of total. In the next few slides, we'll talk about another important comparisons in numbers, ratios and rates. Okay, let's talk about ratios and rates. Ratios is when you're comparing two numbers from two different categories. Don't worry about these numbers. Let's say you're interested in the salary of teachers and engineers average. So the average annual income in thousands for teachers is 65K, and the average income for engineers is 100K. Now, one way to make comparisons between these two for a given year is by ratios. So you can take um, you can try to see how much more do engineers earn when compared to teachers, right? So you take 100 divided by 65, then it will give you 1.54. So the ratio is 1.54 is to 1, meaning for every $1 a teacher earns, an engineer earns 1.54 more. Does it make sense? So $1 equivalent to $1.454. And these ratios are more meaningful. For instance, most of the universities provide their teacher to student ratio. The teacher to student ratio is 2 is to 1, meaning 1 is to 2, meaning that for every one teacher there are two students. And the closer, the smaller the ratio is, the more qualitative the education is. It's a yardstick they measure. So ratio is when you take the max number divided by the small number, and whatever number you come up with will give an indication of um, the how much difference there is in terms of the times, and it's usually compared to one value of um, one category, engineers or teachers, to the potential values of the other category. In this case, it is engineer. So for every $1 engineer earns, teacher earns, an engineer earns $1.54. So in the next slide, I'll give you another example of ratio followed by an example of rates. Okay, so let's take a look at another example for the ratio. Remember, in ratio, you have two numbers that you're comparing, um, and the two numbers, um, the comparison is in ratios. Usually one is at 1 and the other one is at like 20 is to 1, saying there is one teacher for every 20 students, and so on and so forth. And sometimes comparison with 1 is not so meaningful, and it is usually, remember, 1 for proportion, 100 for percentage. These are like standard ways. So ratios are usually done in 1, but they're also done in hundreds depending on the context you're in. And this context that we're going to talk about now is the ratio of observed case and fatality. Observed case and fatality ratio. So what it means is that what is the ratio of observed case and fatality? So um, there are more observed cases and then there are fatalities. Now, observed case here is, this is the COVID-19 current data. that I've downloaded from the Johns Hopkins University site, and it shows how different countries have different observed case fatality ratio. And let's try to understand what it means. Now, if you look at this, this is a mortality rate observed case fatality ratio, meaning that it is 9 point, it's almost, let's say 10. What it means is that for every 100 cases of observed COVID-19 cases, there are 10 people who are dying. Or you can also think of it as 10 is to 1. For every 10 observed cases, there is one death. Does it make sense? Okay. Let's look at this one. Right? Iran has observed case fatality ratio of 5.4, meaning, what does it mean? Can you think? Well, for every 100 cases, 5.4 individuals are dying, right? Now, what about Italy? And you can see Mexico is the highest. The mortality observed case fatality ratio is pretty high in Mexico. And in fact, um, India, if you look at it, it is low. It's 1.5, meaning that for every 100 observed COVID-19 positive cases, approximately 2 people are dying. Okay, and the United States is right here, 2.2. So these are the worst hit, meaning that the ratio between the number of cases versus number of deaths is pretty high. Okay, so this is about the ratios. Usually you can always convert 400s into ones. You just basically need to go to the smallest fraction, and that gives per one. In the next slide, we'll talk about the same slide, but in terms of deaths per 100,000 population. Now remember, here we're talking about the ratio between those who got infected, in other words, tested positive, and of those, how many died, right? Here we're talking about the population in general. What percentage of those populations are actually um, dying because of COVID? Okay, this is about the rate. It's like a rate of death in general because of COVID. And if you look at it, what it says is this rate is per 100,000 population. How many people are dying as a function of the country for every 100,000 members in the population? Now, this is about the population, irrespective of the infection. In general, if you take a country and look at the population and see how many among them are actually dying of COVID-19 complications, that is the number we're talking about. So in Belgium, it is 126.26. In other words, 126 or 100, let's say 120 plus people are dying for every 100,000 people in general, and they're dying of COVID. Make sense? Um, the least is India. It is interesting that it is 9.6. So roughly 10 individuals out of every 100,000 individuals are dying in India out of COVID or because of COVID. And if you look at the US, it is right here, right? It's like 75 people out of every 100,000 people are dying because of COVID. Now, it is important to understand that the kind of knowledge you can gain from this will come from the context. You have to look at the density of the population. You have to look at several other factors. The interesting thing here is that India is a very densely populated country. In a very densely populated country, you would expect more infection rates and more deaths per population. In a less densely denser areas, you would expect less infection rate, and you will expect less deaths per the 100,000 population here. In both these cases, India is an exception here in the sense that it is not at the top in terms of the ratio we talked about earlier, but it is at the bottom when it comes to the deaths per 100,000 population. There is something, and there are several theories on this why it's the case. Like, this is not the place to talk about it, but these are the things. This is how you can kind of, we talked about the data, information, knowledge, right? So this is information to knowledge kind of thing where you're contemplating and kind of deriving some important information out of it. So rate and ratio are different um, ways of comparing numbers. In If you compare two numbers in general related to COVID-19, then deaths versus number of cases, that's ratio. And if you're comparing it to overall population in general, that's the rate. So, okay, I hope you had fun. Okay, benchmark is a kind of comparison where you're comparing your numbers with specific numbers of interest, either within your data or outside of the data. And we'll talk more about it in the next slide. Okay, so coming to benchmarks. Um, when you say benchmarks, you're basically talking about uh, a different kind of comparison between numbers. So if you're comparing your numbers coming from your own data, so average spent on defense versus spent on social security, and if it's coming from the same data, that's called internal benchmark. So the numbers that you're comparing are coming from your data. External benchmark is when you're comparing your numbers with some other numbers outside of your data. For instance, one source would be that you have a 2019 report from a government agency on the number of crimes in a city. Then you have collected data for the current year, and this data set is specific to 2020. But there is a report out there that has summarized the data so far till 2019 or just 2019. When you're comparing the numbers from your data that is specific to 2020 with the data report that is stated, then you're making an external benchmark comparison, meaning that you're comparing your summaries with the summaries from outside of the data. And again, you'll know later on why these are important in specific context. Okay, in the next slide, I'll give you details of the practice exercise, which is optional. Okay, for this optional practice exercise, download this particular Excel file from this link specific to the chapter 9, and then open it and inspect the file and see um, where it contains data about crimes as reported by United States citizen to the FBA, along with populations. Name and explain 3 number comparisons that you could make to generate some meaningful statistics. So I hope you do it.